Hello again. In example 2 here, we're going to do the same thing, but for a different kind of function. In example 2, we're going to investigate what's going on with this function here, f of x equals 1 over 4 minus 2x. We're still just going to find whether the function's increasing or decreasing. And the process is going to be the same as in the previous example, just with different details, of course. So the first thing that we want to do in all cases here, whenever we're talking about increasing or decreasing, the thing that should come to mind, the tool to determine the intervals where the function is increasing or decreasing, the tool in calculus class is the first derivative. This does not mean graph the function and just read off of the graph where it's increasing or decreasing. We want to use critical numbers and just our brains, no graphing calculator to determine this. So the first thing that we want to do is get the critical numbers, which will require getting the derivative. Now, all the derivative rules that we've learned so far still are necessary from here on out. Like for the rest of the semester, we will need those derivative rules. So finding the derivative of something like this, it is a quotient, and it would not be wrong to use the quotient rule on this. However, the numerator of this quotient is a number. There's no variable in the numerator. There are only variables in the denominator. When that's the case, there is an easier thing to do than use the quotient rule, and that is to bring up the denominator into the numerator by negating its exponent, which in this case is a 1, and using the chain rule or the general power rule on this function instead. Okay, so to find the derivative here, using the general power rule, we're going to bring the -1 down in the front and multiply. We leave the base the same. We subtract 1 from the exponent. And then we have to multiply this entire thing by the derivative of the base, or the derivative of the inside function. So the derivative of 4 minus 2x is -2. Now we're going to want to work with this derivative, like use it for a purpose to tell us something. And so simplifying it's going to be something that we will appreciate in the future in just a minute. So to simplify this, we can always multiply this number out front with the derivative of the inside here. So -1 times -2, that's +2. And negative exponents are generally not too simple. So I would rewrite this with that 4 minus 2x in the denominator and make it +2 power. And up top, we have that 2 still hanging out from being multiplied right here. So that one stays up top, does not get to go down into the bottom. All right, so the next thing we want to do is locate the critical points or the critical numbers. And remember, there are 2 types of critical numbers. One of them is where the derivative is equal to 0. So when you're solving for the derivative equal to 0, I mean, it's exactly what it sounds like, right? We're just going to take our derivative and set the whole thing equal to 0. Set the whole thing equal to 0. There should be an equal 0 there. It's there, it's coming, I promise. It got stuck somewhere in the air, I guess, between the iPad and the computer. Okay, so when you're trying to solve a fraction, there we go, set equal to 0, there are a few different ways that you can think about this. The probably most straightforward way is just to get rid of the denominator because you can multiply both sides by the denominator. So if we just do that over here, that's just going to cancel what's in the denominator on the left-hand side. And if we do that on the right-hand side, which we would have to do as well, all that stuff times 0 just gives us 0 on the right-hand side. Another way to think about this is just cross multiplying. If you think about 0 as being 0 over 1, we can cross multiply. 2 times 1 is 2, and then the denominator times 0 is 0. Now that gives us 2 equals 0, and of course that's not true. So there are no values where this fraction is going to be equal to 0. There is another time that critical numbers, or another place they can come from, right? And we can't forget this either. This is 1/2 of the definition, is when the derivative is undefined. Okay, now remember, this is when the denominator of the derivative is equal to 0. And this does actually apply to this situation because we have a derivative in our denominator. So we're going to set the entire derivative. Sorry, that's not right. Not the entire derivative, the entire denominator equal to 0. Now, if your thought is to like FOIL this out and try to solve it that way, pause for a second, because we already have a nice factored thing on the left-hand side. To get rid of that square, FOILing would do that, except you would get an x squared. Then you'd have to factor it again, though, to set it equal to 0. So when something's already factored like this, it's in its best form. And the way to get rid of the square here would just be to take the square root. That just gets rid of that square root. And then we would get technically plus or minus 0 on the other side, but 0 doesn't have a sign, so we'll just say that that's just 0. Okay, then we can solve this for x by maybe just subtracting 4 over and then dividing by 2. It looks like we have one critical number of x equals 2. All right, so now what we do with that critical number is we want to make a sign chart for the derivative. So a sign chart for f prime of x. Okay, this is like again, a fancy number line. So we're going to draw not a super tiny one, but it doesn't have to be massive either. Here's just a decently sized number line. And we're going to put our critical number on the number line. So we've only got one of them. So that's going to split up our number line, or our x values, into 2 different intervals. All numbers less than 2, and all numbers greater than 2. Now remember, why are we doing this again? So the 2, the critical number, this is the only place, the only possible point where the original function here could possibly turn around, right? So in finding that place, that means that all we need to do is check on either side of that number what the sign of the derivative is, because that will tell us whether the function here, the original one, is increasing or decreasing. The sign will be the same on either interval for all x values, but at 2, we've got an undefined derivative, so across that place, we could have a change in sign for the derivative. Okay, so now we want to get to testing some values. So we want to check the sign of f prime on each interval. So that's what's going on over here. Okay, so we want to pick some test values. So how about a number that is less than 2? You could pick 1. I love plugging 0 into stuff, so I'm just going to pick 0. You could pick whatever number though you'd like, -1, -2, any number at all, as long as it's less than 2. And by test, remember what we're doing is we're taking that x value and we're plugging it into the derivative. It's really important to know where we're plugging stuff into. Right, we want the sign of the derivative, so we want to plug that into f prime here. Okay, so it'll be 2 over 4 minus 2 times 0, whole thing squared. So that gives us a 2 up top. In the bottom, we've got 4 minus 0. That's 4, and then we're squaring it, so that's 16. And yes, this is 1 over 8, but I don't care at all about the number. I just care that it's a positive sign. That's all we want to, that's all information we want to extract out of this. Like, it's great and amazing that the slope of the tangent line at 0 is 1/8 or 2/16. But remember, we want to say something about all of these x values, not just 0. And so we conclude that for any x value in this range, the sign of its derivative or its slope of the tangent line will be positive. All right, now we want to test a number that is bigger than 2. So how about 3? We're going to plug that 3 into the derivative function. Up top, we'll get a 2. Down bottom, we've got 4 minus 6, which is -2, and then we're squaring that. And so that's a 4. Now again, this is 1/2, but I only care that this is a positive value. Okay, so what this means is that the function's increasing before 2, and then it continues to increase after 2. So let's conclude, make our conclusion. Very important step here. Basically interpret the sign chart. So we would say f of x, the original function, which was 1 over 4 minus 2x, is increasing from -infinity. Now, if you're wondering, can we put these together? Like, can we just say -infinity to infinity? Because it's increasing. Oops, I just threw my electronic pencil. It's just increasing, you know, for all numbers. But it's actually not, because at 2, the derivative isn't positive. The derivative is undefined. And so it's actually not increasing at the point 2. But everywhere else it is, right? So the way that we would notate that, we would say -infinity to 2 and 2 to infinity. And I think I missed an on here. Increasing on. Okay, so again, let's just kind of check and see by graphing this function and making a sketch maybe next to our sign chart so that we can see, you know, what this means in terms of its graph. So I'm going to set up my axes. And remember, we're graphing the original function, not the derivative. And again, pull out your calculator or pull up Desmos or any other graphing website. And here's the graph of that thing. It's got a vertical asymptote, it looks like at 2. That makes sense. The derivative was undefined there. Actually, the whole function is undefined there, right? The bottom is 0. It's got a non-removable discontinuity. There's no point on the graph to have a tangent line, so there's no slope. And you can see how the function's increasing before 2. Then it continues to increase after 2, right? It's going up the whole time. It just does something weird at 2, right? There's a break there or an asymptote. Okay, so let's go ahead and sketch that in next to our sign chart here. So here's 2. We've got a vertical asymptote there. The function looks something like this. Like this. And again, it's increasing before 2. And then it's increasing after 2. But at 2, it's not. Okay, so I've got 2 more examples for us. This is a nice example where we have an undefined derivative or an undefined slope somewhere, and how you can see kind of examples of what that might look like. In the next 2 examples, we've got a combination of things going on. They're super interesting, fun graphs. So tune into those, and I will see you then.